All right, it says we're recording. So we are going to go over chapter 3 today. And well, I guess I'll show that quickly. There was our breakdown of grades. Chapter 3 deals with the normal distribution. Okay. So all that good hard work that you did on standard deviation is going to now come into fruition. So the normal distribution is the most common type of data. Many other distributions can resemble the normal curve, and often we draw a smooth line over our histogram to see if it resembles a normal distribution. So normal curves are predictable, and we often use a table to calculate the area under the curve for different situations. So 4 things that we should remember. The area under a normal curve is 1 or 100%. In a normal curve, the mean equals the median in the normal distribution. It's symmetric. And the 2 most important numbers are the mean and the standard deviation. Those numbers completely specify the curve. Now,
Are you sharing your screen? Because I don't see
am I
the
not
picture.
sharing the screen?
No.
Oh. Well, thank you for letting me know. I thought it was. Okay. Guess we didn't get to look at that thing then. Oh, where is it? There we go. That's what I was trying to share. Okay. So so we actually have a fantastic rule called the 68, 95, 99.7 rule. And so the idea with that rule is 68% of your data are within 1 standard deviation on it. This is only for the normal curve. Excuse me, 95% is within 2, and 99.7% of your data are within 3. And so here we go. Let's go ahead and I'm going to open this up. All right, so if we have a normal curve here, your normal curve looks like your famous bell curve that we were all. Wow, I'm getting really good at drawing these normal curves because I used to draw terrible. Okay, so one of the nice things we said is the normal curve is symmetric. So here, I'm going to draw a better line. If I do that, then that's a straight line. Okay. All right, so you're going to have 50% of the curve on the right side, 50% on the left. This line that I just drew is the population. Oh, you know what? I'm going to put MU because I don't draw Greek very well. Do I have that in here? I'm going to be showing you this formula here shortly, in fact. So actually, we'll talk about both of these formulas. I'm going to copy this over here. So, oh, that was lame. It didn't copy the formula. Okay, this Greek letter mu here looks like a U with a tail on the front side of it. I just want to highlight the letter, this letter here. That is the Greek letter mu. And so it's hard for me to write in Greek, so I'm going to put mu for mu, but that's the Greek letter mu. So the idea here is if I go out 1 standard deviation, so 1 sigma, oh, well, that's fine. No, I want you to do that in black. Okay, so if I go out 1 standard deviation, so if that's the Greek letter mu, and then if I go out sigma, so sigma is going to represent this letter down here in the denominator, okay? So if I go out +1, -1 to +1, And now I'm going to fill in my data with this here. So this area here represents 68. I'm going to try it out this way. 68% of the data in a normal distribution. Right there. Okay. And so the idea here is, if you can, in fact, I can guarantee you this will be a test question. I'll give you a bunch of numbers here and I'll say I want you to draw the normal curve. Okay. If I go out 2 standard deviations, so from here to here, so and generally I probably should have put a sigma there. So if I go from -2 sigma to +2 sigma, we'll do that in blue. So this area here, from -2 sigma to +2 sigma, that area in blue represents 95% of your data. Okay, so that would be the blue and the red. And if I go out 1 more standard deviation, I didn't mean to make that blue, but we'll leave it for now. And then we'll go with green here. This, well, we didn't need to do that, that's all right. So this here is going to represent -3 sigma to +3 sigma. And so that represents 99%, 99.7% of the data. Okay. And so, so normal curves are extremely predictable, and we can know that a normal distribution will follow this. Okay. So one of the things that we can do here is we can say, okay, the nice thing about a normal distribution is we can convert it to a standard normal table. And we can say, okay, who had the better score? So Jenny scored 600 on the SAT exam, and her friend Gerald scored 21 on the ACT exam. Okay. So the SAT is normally distributed with a mean of 500, and it has a standard deviation of 100. Okay. So I could actually draw that on here. And so the idea here is, maybe I will, here's what I'm going to do. I'm going to remove all of these values here. And so the idea here is, what we can do is, so if we know that the SAT score, here, I'm going to copy that. Here. Okay, so the SAT score is normally distributed with a mean of 500 and a standard deviation of 100. So the idea here is, you can draw this on here, and if this is your mean score, so I've got a mean of 500 and a standard deviation of 100. So I know that 68% of students are going to be between the scores of 400 and 600, okay, according to the 68, 95, 99 rule. And I know that 95% are between the scores of 300 and 700. And I know that 99% of the scores are between 200 and 800. Okay. So just knowing the mean and the standard deviation, you should be able to label a normal curve just like that. Okay. Now, here's what I'm going to do. I'm going to make a copy of this. I'm going to slide that over a little bit. Okay. And I'm going to make another curve here. Now, in fact, I might make another one. Okay, this time I'm going to erase the scales. I should have done that, but I didn't. Okay. Now, so we also know that the ACT is normally distributed with a mean of 18 and a standard deviation of 6. So what I could do here, I'm going to copy this. I'm going to paste this. We're going to do the same thing over here with the ACT scores. Okay. So since you've seen me do that for the SAT, who do I want to pick on? How about Elise? Can you help me draw the numbers for the ACT score?
Oh, I'm not sure about that one.
Okay. So it says it has a mean of 18. So based on this graph here, would I draw the 18 on which line?
Is this a question for anyone, or was this still for Elise?
Sure. We'll let anyone bail out Elise.
Okay, I think it goes on the middle line.
The middle line, that is correct. Okay, so we know that the mean score is 18, and so the mean, this is the population mean, that's always going to be the middle line on your bell curve. Okay, now we know that we've got a standard deviation of 6. So I'm going to add and subtract 6 to there. And so what is the value? So Elise, since you got bailed out by Janie on that one, if you subtract 6, what should this value be here?
On the third line?
Yes. What's 18 minus 6?
12.
12, very good. And what's 18 plus 6?
24.
24. So according to the 68, 95, 99 rule, 68% of the students scored between a 12 and a 24 on the ACT exam. Does that make sense?
Yes.
Okay. All right. So now let's go to Allie. Allie, can you tell me what the scores for 2 standard deviations should be?
Like the next line?
The next line, correct.
Yeah, that's should be 6.
6 and
30.
30. So what percent of students scored between 6 and 30?
95%.
95%. Okay, well done. And then Bridger. Bridger's microphone never works. Is it working today, Bridger? Can you make some sort of a text or something to let us know you're listening? Because you don't get full credit if you don't listen. If you just show up and walk away and don't have your camera on, you don't get credit for being here. All right, Bridger, I hope you're just having a microphone problem, but we're going to move to Easton. Easton, can you give me these values here?
So wouldn't that one be 0?
0 and
36.
36. Okay, so what does that represent?
99.7% of the data.
99.7% of students scored between 0 and 36 on the ACT exam. Okay. Okay, so the nice thing about this is you can see here, so let's say, do I have that on here? Okay, so I'm just going to make up some numbers here. Okay, so let's say that Jenny, here we unlike that, let's go with black. Jenny scored 600 on the SAT, and let's say that Easton. Here, we're going to pick somebody else that's in the class. Who are the next two people here? Janie and Seth. Are you here, Seth?
Yeah, I'm here.
Okay, cool. Okay, so we're going to pretend these are your scores. So who did I say? Janie is close to Jenny. Janie scored 600 on the SAT, and Seth scored 21 on the ACT, and we're going to say who did better. Okay. Can you guys tell now that we've drawn these pictures who did better?
Yeah, Janie.
Why do we say Janie did better?
Hers was up. Would it be because hers was up higher on the scale of?
Yeah, so she's right exactly 1 standard deviation above.
Yeah.
Whereas Seth is not quite, he's in the middle here, right? This is Seth's score. Seth's got a 21. Okay. Now, it might be interesting to, so you can kind of tell just by drawing this out here and putting the values in here, you can see that in this case, Janie did score better. Okay. Visually see, but it would be nice, wouldn't it, to put them both on the same scale so you could see their scales better. Okay. And so the idea here is we can do that with what's called the standard normal distribution. Okay. Now this is one of my favorite questions to ask, and students will miss it. Okay. Because they don't realize that this is a special distribution. Now, the idea with the standard normal distribution is it has a mean of 0. Now, one of my favorite test questions is, what is the mean for the standard normal distribution? And a lot of students will say, I don't know, you didn't tell me. I'm telling you today, when I ask you about the standard normal distribution, okay, this thing here, the mean is always 0 and the standard deviation is always 1. Okay, so this would be +1, this would be -1. And so therefore, this is +2 and -2 and +3.
And that's when you see the term standard normal distribution?
Correct. Okay. So the standard normal distribution is a special distribution. It always has standard deviation of 0, a mean of 0 and a standard deviation of 1. Okay? And so what's really nice about that is if we go back to our maybe I should put this in here. If we go back to our announcements, okay, on this next test, okay, we've got the formula sheets and tables here. And so page 1 you're very familiar with because you could use it on the last test. Page 2 is the random distribution table. Page 3 is your standard normal distribution, okay? So this is the table. I want you to memorize this table right here, okay? Can you guys do that by next Friday? I got a smile out of Easton. The rest of you aren't on camera. Yeah, you don't have to memorize that, okay? I'm just teasing. So anyway, you guys are a tough crowd, especially when you're not on camera and I can't even see that you're smiling and you know that I'm kidding. Okay, so this is what we call a standard normal distribution. So the idea here is, especially in this case, so Janie, we can know that Janie is exactly 1 standard deviation above the mean. And so the idea here is, even with these, what's nice about this, because Janie scored 600 on the SAT, okay, we can also use this to figure out, in fact, who did better. Okay, so we can answer that question. We know that Janie did better. But Janie's probably more interested in knowing that what percent of students did worse. Okay, because she wants to know that. So here's the nice thing. Because the data are symmetric, okay, I know that below 500, this area to the right here, or to the left here, I know that that is 50%, right? Okay. And because it's symmetric, I know that I've got 34% here, and I've got 34% here. So if I split that in half, then basically I can say that, oh, in this case, 50 plus 34% means that Janie did better than 84% of students. Okay? Does that make sense? Okay. Now it's a little bit tougher because in Seth's case, okay, Seth doesn't fall on one of the nice standard deviation curves. Okay. And so we can't really do, so we can do that with Janie. We can figure out what she did with the 68, 95, 99 rule. And in fact, there will be a lot of questions about this. So we'll probably start doing some more questions in just a minute. But in Seth's case, we can't really do that because Seth is in between the values. Okay. So the idea here is, Seth probably wants to know how better he did. Now we do know the same thing with Seth in this case, in that we know that from here over, that represents 50%. 50%. Now the question is, what's the difference between 21 and 18? Well, we know it's less than 34%, and you might be tempted to say, well, I'm going to split that in half. No, don't do that, because the problem is it's a curve, it's not a straight line. So we know that he scored somewhere between better than 50% of students and better than, but he didn't do as well as 84% of the students. So the answer is between 50 and 84. So in our here. Okay. So here we go. So we can, here we go. We can standardize scores with this formula here, okay? So in the book, they have this formula, z equals x minus mu over sigma. So a lot of the times on this third distribution here, we refer to this as the z distribution. Okay? And so the standard normal distribution is the z distribution. And so we can use this formula x minus mu over sigma. Now, the problem is we've got this formula z equals x minus mu over sigma. And then later on in the semester, probably in a chapter or two, I don't know if it'll be before or after this next test, but we're going to learn this other formula, z equals, oh, actually, this isn't really, well, it is there. Z equals mu over sigma over the square root of n, okay? So this is the formula you're going to use in chapter 3, and this is formula you're going to use in a future chapter. And what's going to happen is students are going to get mixed up, and you're going to say, well, which formula should I use? So what I'm going to tell you is use this formula, okay? And we can use this on Janie, okay? So the idea here is, so my z equals, somebody's got a loud buzz that's making a lot of noise. But z is going to equal x minus mu, thank you, that went away, over sigma over the square root of n. Okay, I'm going to underline that so that it looks like a fraction. Okay, and so the idea here is we can convert any normal distribution to a standard normal distribution by using this equation right here. Okay, so this is the equation. I know it's actually on your formula sheet here on the first page. Right here. There it is. But you'll probably use it so much for the rest of the semester, we're going to use this equation a lot that you'll probably kind of start to memorize it. So one way to think about this, if you think about this in terms z, oops, I didn't mean to underline that. Z equals so x represents your data minus your mean over what happened? Just want to keep typing. It won't let me type. Okay, well, forget that. Over this sigma, I don't want it to underline anymore. Sigma over the square root of n. So that's kind of conceptually what's going on here. Is this right here, okay? And so the idea here is if we do this, I think Seth answered last time, so it must be Janie's turn. Can you plug in all of the information that we've got in here for your this equation here? So what do you think x is, Janie? And if maybe you're on mute because we didn't hear you say anything if you've said anything.
Is x the mean?
No.
Oh.
X is the data. So what's your data?
So is that the 600?
That would be the 600. Okay.
Okay.
So you scored 600. And we're going to subtract mu. What's mu?
I have no idea. Oh, is that the mean?
That's the mean of the SAT score.
Okay, so that's 18 then.
That's 18 is for the ACT, but you took the SAT.
Oh, okay. I'm following. 500.
500. Okay. And we're going to divide by what? What's sigma?
Yeah, and the square root of.
No, let's do sigma first.
Okay, I'm so lost.
What does sigma represent? You should have known that for the last test.
Yeah, shouldn't I? I have no clue.
You want to phone a friend?
Okay.
Okay, friends, she's phoning you guys. What's sigma?
Standard distribution.
Standard deviation.
Deviation, sorry.
What's the standard deviation, Janie, on the
Oh,
SAT
it's
exam?
100.
100. And how many Janies are there?
Hint, you're unique.
Oh, so there's only one of me.
There's only one of you.
Yeah.
I thought that was an easy question.
It's early in the morning in California.
Oh, are you in California?
Yeah.
Wow. Oh, yeah. Well, yeah, it is early. Sorry.
You're
That's what
good.
you get
You're
for
good.
taking an early morning mountain time class.
Yeah.
All right. So, okay. So we've just done that. And so now we can simplify this. And so the idea here is Z is going to equal 600 minus 500 is 100. And 100 divided by the square root of 1 is 100. So 100 divided by 100 equals 1. And so now what we've done is we've converted Janie from this normal distribution here, this one here, okay? We've now converted her to a standard normal distribution here. And so now we will put a J right here so that we know Janie scored 1 standard deviation away. Okay? So since we've done that, Seth, can you do the same thing for your SAT exam?
Yes.
Okay. Z is going to equal.
Be 21 minus 18, and then divided by 6, divided by 1.
Sorry, I forgot to turn off my underline here. 6 divided by the square root of, there's only one Seth, okay? And so that gives us a Z score of, on the numerator, Z equals, on the top, 21 minus 18 is 3, and on the bottom, 3 divided by 6. So that is going to equal Z equals 0.5, okay? So the idea here is Seth is a half of a standard deviation here. So if we put this in here, so 0.5 standard deviations away, that is going to be Seth's score. So you can, the cool thing is now we can compare Janie directly to Seth, and we can say, oh yes, so Janie scored higher on the standard normal distribution here, okay? Now, the question is that Seth still wants to know, he knows he did better than 50% of the people who took the SAT, but he doesn't know exactly what percent like we did with Janie, because Janie was on exactly 1 standard deviation. And so the idea here is what we can do is we can go over here to to our formula sheet, and then you've all memorized this page here, right? Okay. So the idea here is I've got z-scores down this blue column here. And so what I need to do is I want to find 0.5. And so 0.5 is right here. And so we can see that to 4 decimal places, Seth scored better than 69.15%. So these are all decimals. You can think of these as percents. And so the idea here is we can say that in this case, Seth scored better than 0.6915 or 69.15% of students took the ACT exam. Okay. So while it was fairly easy, we could use the 68, 95, 99 rule for Janie. We couldn't really do that with Seth because he didn't fall on one of those numbers there. So does that make sense? Okay. So what I would like to do, oh, I forgot we meet for 2 hours. But we're going to spend probably the next hour making sure. Hopefully, I'm going to drill this into you guys' heads. I might keep this here. I kind of like my page.
Professor Bennett,
yes, go ahead.
My internet cut out on me there just a minute ago. So how did you get from the 0.5 to the 69.15? Did you use the chart? How did you get to half?
I did.
Okay.
And in fact, we're going to do more of that in just a minute here. Oh, I need to get rid of that. I'll fix my notes. Okay, so here's what I would like to do. Well, actually, before I do that, here's what I would like to do. Oh, I'm missing the problem that I usually give you guys. I'm looking for it and I don't see it. Oh, okay, well, I'll just make it up then. I'm going to start with a new page here. Okay. Let's say that the height of women is known to be normally distributed, and the mean is 68 inches tall with a standard deviation of 2.5 inches. Okay. Now what's nice about this is I can give you this information and then I can ask you about 20 questions about this. So let's say that the first question that I want you to do is find the or draw a normal curve illustrating the 68, 95, 99.7 rule. Okay. So whose turn is it? It must be Wes's turn. Can you do that?
Yeah.
Okay.
Go ahead and create your beautiful bell curve that you're getting so good at drawing.
Okay.
All right, right there at the apex, we'll go ahead and put the mean.
Okay. What's this value here?
It's 68 inches.
68 inches. Okay.
And then we'll go ahead and draw our first standard deviation.
Okay. What are these values here?
On the lower end, you got 65.5. On the upper end, you got 70.5.
So 70.5, and on the lower end, 65.5. Okay.
Now draw our 2 sigma line.
Okay.
And we'll have 73 inches on the upper one there.
That was not supposed to do that. I forgot to draw my thing here. Okay. This value is 73.
Yep.
And this value?
Would be 63.
Okay.
And then draw our 3 sigma. And you'll get 60.5 on the lower end. And 75.5 on the upper.
$25.5. Okay. All right. Well done. Okay. All right. So now, what I want to do, there's 2 ways to do these problems. And so I want to get you used to first using the 68, 95, 99 rule. And so question B, how tall, or maybe let's do it this way. What percent of women greater than 70.5 inches tall? Okay, so these questions are going to get progressively harder. So you're going to wish that you were already called on. But Yami, can you tell me, or can you answer that question?
So we're assuming 68 is 50%. So above that of 70.5, is it 84%?
Okay, you remember that from the last problem. Okay, so very good. So you know from the last problem, here we're going to pick a different color though. Okay, you know that this below is 50%. And you know that this is 34% in here. Okay, so 50 and 34 is 84%, and so we're really looking for this value here, right? So what is that value in red?
I'm not sure.
Well, you know that 84% is in white, essentially, right? And you know the area under the curve is 100%. So what's 100 minus 84?
Oh, 16.
So very good. So that would be, so your answer here is 16%. Okay. Well done. How about, percent of women are taller than 73 inches? Okay, so now we're back to Elise. Do you know how to figure that out? Elise, are you still with us? I didn't look.
Yes.
Okay, good. You were just thinking.
Yeah, I'm still looking.
Any ideas?
Not really.
Not really. Okay. So here, let me ask you another question that I think you know the answer to, and hopefully that will help you with part C. So I'm going to ask you part D. What percent of women are between 63 and 73 inches tall? Hopefully you know that answer. And just to illustrate here, I'm going to change the colors here. So if I paint this, so 63 to 73 inches tall, that would be the green area.
Could it be 88%?
88%, how did you get that?
Let's see. I just guessed.
You were just guessing.
Yeah.
Okay, well, you shouldn't have been guessing. Okay, now what we can do is we can convert this. In fact, tell you what I'm going to do. I'm going to draw this picture again. I'm going to cut off all of the values at the bottom here. Okay, now this is now, let's pretend that this is a standard normal distribution. Standard normal distribution. Okay. If this is a standard normal distribution, what is the mean?
Zero.
0. And what is your standard deviation?
-1.
-1, and this on the right would be +1, right?
+1, yes.
-1. Okay. And then this value here is +2 and -2. Okay. So according to the 68, 95, 99 rule, when I'm 2 standard deviations away, which is the green area, what percent of women are between 2 or within 2 standard deviations?
Is it 50%?
Say that again.
50%?
Nope.
75?
Okay, there's a reason it's called the 68, 95, 99 rule. 68% represents what standard deviation? So this here is 68%, right?
Yes.
Okay. So if that's 68%, what's the green area? And I'm going to highlight it right there. It's going to be 95%. Okay. Do you remember that?
Kind of.
We just talked about that. Okay. All right. So the green area here is 95%. Maybe I should do that in green. 95%. Okay. If you've got 95% in this green area here or this green area here, how much is half of 95%? Ali,
it-
do you know?
One second. It's 47.5.
47.5%. So I've got 47.5% on each side of the mean in the green area, okay? So what percent of women are taller than 73 inches, okay? So the idea here is, essentially, I want the red area. So if I've got 47.5% represents this area here, and I know that this area here, all the way to the end, is 50%. So 50 plus 47 is 97.5. So what would be the red area? I'll leave that to anybody who wants to answer.
2.5.
2.5%, okay? So the percent of women taller than 73 inches would be 2.5% of women. Does that make sense, Elise?
Yes.
Okay. What if I ask this question here? What percent of women are 65.5 to 73 inches tall? Bridger, can you answer that? Oh, Bridger, are you there? Bridger, can you email me and tell me why you can't answer? Do you need a microphone or what? Because you're not going to get full credit if you can't answer. Easton, how about can you tell me what percent of women are 65.5 to 73 inches tall?
Yes. Would it be
Okay.
81.5% of the women?
81.5. How did you come up with that number?
So from 68 to 73 inches tall is 47.5.
Okay, so you use this number right here. Okay.
And then we know that from 68 down to 65.5 is 34%.
Oh, that's 34%.
And so then I just added the two.
So you add those two. So 34 plus 47.5 equals 81.5%. So well done. Okay, that's exactly correct. Okay. What percent of women are shorter than 60.5 inches tall. Okay, so we're talking about the short women now. So since Easton just answered that, it must be Janie's turn. Can you answer that one, Janie?
Yeah, I know I think we're supposed to subtract something, but if I'm going to be honest with you, I have no clue what we're going to subtract. Like, would we do 50% minus the 47.5 to get?
Oh, you know, I hadn't thought of doing it that way, but that's a good way to do it. Because, yeah, we know that 50% of women are less than the mean. And you know that between, well, actually, no, because that's not. That was a good guess, but you can use the same sort of an idea, though. Okay, so you ignored the white part. You subtracted the green part, but we've got the white part in there too.
Okay.
So here, let me before we answer that question, let's do this one. What percent of women mean 60.5, 75.5 inches? Do you remember that, Janie?
Is this that rule?
It is.
So would it be 95?
90, not 95.
99.7.
9.7%. Okay. Okay, so we know that 99.7% of women are between here. So what is in both tails? I'm going to highlight both tails here. So both the purple sections. So how much is in both tails? If you've got 99.7% in the non-purple areas, how much are in the purple areas?
I feel like this is such an easy answer and I don't know it. Is it just the 2.5?
So you're jumping to the wrong, you're going to 2 standard deviations, not 3. It's 100 minus 99.7%.
Oh, I see.
Which equals? Oh, you're using your calculator for that?
Yeah, I'm sucky at math. We're going to make this clear now. It's 0.3.
0.3.
Yeah.
Okay, so if you've got 0.3 in both tails, how much do you have in one tail? Half of that, right?
Yeah.
What's half of 0.3?
I'm going to use my calculator, so make fun of me all you want. It's 0.15.
Okay, so in this case, now we can answer the question that I originally asked you in red here. What percent of women are shorter than 60.5 inches tall? And the answer is
0.15.
0.15. 0.15 percent. Okay. Now, if we converted that to a decimal, what would the decimal be? I'll throw that to anybody.
0.0015.
Got 2 zeros on 1 5. Okay. So both of those answers would be correct. One's a percent, one's a decimal. Okay. How confident do you guys feel if I asked you to do this with the 68, 95, 99 rule? Can you ace all the questions on the homework?
I think we just need to do practice.
Yes. Okay, so I've spent about 30 minutes. Maybe we could do one more, but then I want to start working on the table. Okay. So let me see if I can come up with one more question. And what's my question? Oh, here we go. This is going to be a good hard one. So now you can't wait for me to pick on you. Okay. So here we go. This is going to be question E in purple. What percent of women are between 63 and 65.5 inches tall? Do we have any volunteers? Because that one's going to be the hardest one yet.
I'll try it out.
Okay. Is that Janie?
No, that's Allie.
Allie. Okay,
It
go
is
for it, Allie.
Okay, so for
Wish you
this
were on
one,
camera, though.
yeah, okay.
No problem.
So you take the 63 and the 6, like, because up there you have like 47.5, right?
Yeah, so the 47.5 is the green area just below the mean. So you've got 47.5.
So the 63 and the 65 to like the 68, like those are like 2. So wouldn't you just divide it by 2 to find the answer between 63 and 65?
No.
So you wouldn't?
No. So you're correct. So the idea here is, let me draw a box here. So you have correctly said that 47.5 is in this box. That's supposed to be right on 63, but it's kind of hard to read if we do it that way. Okay. Now the question is, what is in this box here? Oh, I should have picked a different color, like blue. What's in that box?
Well, it says 34%.
It says 34%. That is correct.
Oh, so would it be 47.5 minus 34%?
Minus 34%, which would equal
13.5.
13.5%. Okay, you just did the hardest problem.
Okay. So what you have to do first, because like it does like get smaller as it goes like throughout the standard deviation, like what percentage it is. So you first have to find like the half of that.
Well, it's not half.
Well, not
so
like
we can now fill this in because we did this problem here. This area here is 13.5%. Do we know what this area here would be?
The white space.
The white space, yeah. How would you figure that out? We know this area over here because who figured that out? I already forgot. You're Allie, and so that was, oh, I can't remember her name. Janie, sorry, I had to cheat.
Yeah, you tend to mix me and Janie up a bit.
Yeah, it's because you guys aren't on camera.
Sorry.
So we know that this area is 0.15, right? Percent. So what's the white? So you can see these numbers. They go from 34 to 13 to something that we don't know to 0.15.
Yeah, so you
so
just
can
have
we figure out what that is? What is this
you
area
add up
here?
the 34 plus the 13.5 plus the 0.15, and then you subtract that from the 47.5. And
Oh, that's one way to do it. I hadn't thought of that, but yeah, we could do it that way. So 34 plus 13.5 plus 0.15. That equals whatever it equals, and then we're going to take 50 minus that, right? So what is this? I can't. Let's see. That's 47. That's 47.65.
65.
And so 50 minus 47.65 would equal 2.35. Is that right?
Hmm.
Check my math.
Yes.
Okay. So this area here is 2.35%. Okay. So you can see these numbers really go down. So you don't want to be just splitting these in half and half and half, because it's like that's, yeah, it's not even, I don't even know what those are. But anyway, it's a big difference. Okay. I guess we could put 2.35 over here too. Oh, you can't even read that one. But anyway, okay. So there's going to be a bunch of questions on your homework that deal with the 68, 95, 99.7 rule. Okay. Now, to be honest, and this is where I'd like to spend the rest of the class, it's nice when you get a value that are right on one of those spots. But the question then arises, it says, a woman who is 69 inches tall is taller than what percent of women? Okay. Now, because 69 is not part of my rules here, 69 in this case would be this value about right here. Okay, that's not on one of my nice numbers. So how would I answer this question?
Is that when you use the z-score formula?
That's the one where we use the z-score formula. Okay, so z-score formula. So z is going to equal x minus mu over sigma over the square root of n. And that, okay. All right, so how do I do that?
Well, the x is the 69, right?
Okay, 69 minus.
Subtract it by.
You can't read that because it's been covered up, but yeah, 68. That's what it's supposed to be. Okay.
All right, and then you divide it by the sigma, and that would be point. Oh wait, I have to calculate that first.
No, you shouldn't have to calculate that.
Oh yeah, it's 2.5. It's 2.5.
2.5 inches. That's right here.
Divided
Right
by the number. So the number, there's just like one, like we're just looking for the one number, right?
Okay, so here's the trick question. In chapter 3, it's always 1. You're always going to divide by the square root of 1. And so that's kind of why they leave it out in the formula. If you look at these, because the square root of n is always going to be the square root of 1, and so that's why they leave it out here. But just know, well, that's okay. Your n is always going to be 1 in chapter 3. It's not always going to be 1 in later chapters. Okay. So that's why they use this formula, because it's going to fall out anyway. Okay. So essentially what we've got here, we've got a 1 in the numerator, we've got 2.5 in the denominator, and now I can't calculate. I could actually calculate that in my head, but I don't expect you guys to. What is that value equal to when you plug it in your calculator? 1 divided by 2.5.
0.4.
0.4. Okay. Now, okay, so that's my z-score. So now remember, so my z-score equals 0.4. That is not 40%. Okay. What that tells me is, in this case, because I've just converted this to a standard normal curve, and I am now 0.4 standard deviations away. Okay, so if I were to draw that on my normal curve, so we've just converted this number 69 to a standard normal, and so that number corresponds to 0.4 standard deviations away. Okay. Now at this point, I can't use the 68, 95, 99.7 rule. Now I have to go to my chart. Okay. And I'm looking for 0.4. Now, by the way, I didn't finish telling you. So this column here, sorry, this blue column here gives you 1 decimal, and then this gives you the second decimal across the top. Okay. So 0.4, I'm just going to look at the first column. Okay. So 0.4, and oh, by the way, I should mention this. You should look, so this always represents the left side of the curve. So in this case, I want the value that's less than 0.4. Okay. So if I go to 0.4, that gives me this value here, which is 0.6554. Okay. So to answer this question here, what a woman who is 69 inches tall is taller than what percent of women? And the answer would be what, according to the chart here?
0.6554.
Right, 0.6554, or 65.54% of women. Okay, does that make sense? Okay, all right. Do you want me to copy this and put it in our notes?
Yes, please.
Okay.
Yes, please.
All right, we'll put this in my notes here. So, okay, so here's what I would like to do. Okay, let's move on to some other stuff that is not how tall women are. Okay, now, some of you are not baseball fans, and shame on you if you're not, but that's okay. So who had a better year? If the Yankees scored 968 runs, and we're assuming it's normally distributed with a mean of 968 runs and a standard deviation of 73.5 in the American League. In the National League, so the Phillies play in the National League, they scored 892 runs, and the mean is, or the standard deviation is 58.9. Okay, so we want to know who had a better year. Now, here's the problem, okay? For those of you who aren't baseball fans, the Yankees play in the American League, and they're going to score more runs because the pitcher does not have to hit. And so the Phillies, on the other hand, play in the National League. They're going to score fewer runs because the pitcher doesn't hit, or the pitcher does hit, rather. And so the pitchers are terrible hitters. That's the general rule. Babe Ruth is the exception. And so the idea here is we want to compare. We can't just assume that the Yankees are better because they scored more runs, because in the American League, they, oh, you know what? There's some data missing here. The Yankees scored. Oh, you know what? These are wrong. These values are wrong. I can tell. I gotta write this. And 763. Phillies scored 892 runs. Sorry, I just gave away this thing. Okay, so this was wrong. But the idea here is okay. So the idea here is the Yankees are in the American League, the AL, American League, they scored 968 runs, where the mean was just 793. The standard deviation was 73.5. The Phillies scored 892 runs, but their league, the mean was 763, and they had a standard deviation of 58.9. Okay? And so the idea is who was the better hitting team compared to their league. Phillies are in the National League. Okay. Now, I've already got the answer here, but what I would like to do is I'd like to do this fresh. Okay, based on this. Oh, sorry. I forgot that it doesn't copy. This is the mu. This is the standard deviation. So I apologize, that didn't copy. Okay. So, Wes, are you a baseball fan?
Yeah, I used to be when I was a little kid.
Who's your favorite team?
The Mariners, which are in the American League.
They are in the American League. So you hate the Yankees?
Yeah, not a big fan. Not
okay, that makes me happy. I'm a Red Sox fan, and normally when we get into class and I say anybody who's wearing a Yankee hat, you've automatically failed the class. Okay.
I like it.
So anyway, so Wes, can you help me figure this out? We need to find the Z score for the Yankees. So I'll put Z for the Yankees. And I don't know why I picked this. The problem was this was a book problem and they picked the Yankees. I would have picked the Red Sox because they're much better. Okay.
So their data set is going to be 968.
68. 968, I can't type. Minus?
The standard deviation, or the standard
mean.
deviation would be 70. Oh, minus the mean? Yeah, 793.
793.9. Okay. We're going to divide that by?
The 73.1.
Divided by the square root of how many Yankee teams are there?
There's just one.
Only one. Oh, that's good. We hate the Yankees. Okay. All right. So we can plug this in to our calculators and tell you what I'm going to do. Because Excel is the greatest calculator ever, I'm going to use that one here so you can kind of see here. So this is 968 minus 793.9, and this is 73.5. Oh, there's one divided by the square root of 1, so that's just that. So this is going to give me this divided by that, which is a z-score of 2.368. Okay? All right, so 2.3687. Now, so this is going to round to 2.37. Okay? Now we're going to have to go back to our chart here. We're going to find 2.37. Okay, so 2.3. Okay. Now up at the top, you've got 0.07 as this column here. So we're going to be looking at this column. And in fact, you know what? I'll tell you what I'm going to do. I actually have something where it won't erase the column headings if I can find it. Tables. Okay, so we've got our normal distribution here. Okay, so the nice thing is, so we're going to 2.37, which is going to be that number right there. Okay, So what we can say is that the Yankees did better than 99% of the teams. Okay. So your Z-score was 2.37. So your Z-score equals 2.37, which corresponds to a value of 0.9911. Okay. All right. So Seth, are you a baseball fan?
Not a big baseball fan. Sorry.
Okay. So you don't care if the Phillies are better. So now, can you help me figure out the Z-score for the Phillies?
Yeah.
Okay. So how do we do this?
So it'd be 892 minus the 763 runs.
Okay.
Divided by 589, and then their score root for now is always going to be 1.
Yeah, there's only one Philly team. Okay. So we will plug that in our fancy calculator, and we're going to see here. Okay. So that's going to be 892 minus 763 and 58.9 divided by the square root of 1. So that's going to be this divided by that, which is 2.19. Okay. So you can see if we were to convert this to a standard normal distribution, in fact, I may still do this. Okay. You can kind of tell just based on the Z-scores who's the better team. What did we say the Phillies were? The Phillies are 2.19. So Z equals 2.19. So as we draw our fancy bell curve here, okay, so we've just converted the Yankees and the Phillies to the same mean. What is the mean with the standard normal curve?
Is it 0?
0.
It is 0. Okay. And so if we draw this on here, the Yankees are at 2.37, and the Phillies are very close, but they're not quite as high. They're at 2.19. Well, those numbers are right on top of each other. Sorry about that. And so who did better?
The Yankees.
Those damn Yankees. We hate the Yankees. Okay, so the Yankees are better.
I'd like to see it on a dollar cost averaging.
All right. So but we didn't figure out what the Phillies. So the Yankees, we figured out their p-value was 0.9911. Can you guys figure out what the value is for the Phillies?
I think it's 0.48.
0.48?
Because I did 2.1 and then I went to 0.09.
Okay. So you've got a 2.1, and then they're 2.19, aren't they?
Oh,
so
yeah.
2.19. So that should be this value here. So that's 0.9857. Does that make sense?
Yes.
Okay.
Question. So these numbers on the table, like what exactly is the significance of those numbers? Like what is...
Okay. So here I'm going to draw, the Phillies are a red team, and so we will draw this in red. And so the idea behind this is, okay, the area to the left of the Phillies, okay, so the area, oh, we need a different color than red. Red on red doesn't work. The area to the left is what did they say? 0.9857. Okay. So the idea here is the Phillies did better than 98% of the teams in the National League. 98.5% of the teams. Okay. And so the Yankees did better because they did better than 99% of the teams. So if I count, I don't like their colors, so we're going to make them orange anyway. Okay. So if you count the area in the orange and the red, the Yankees did better than 99.11, than 0.9911 of teams.
And you said that number was called the p-value, so that's like the
percentage. That's what we call the p-value.
Okay.
Okay. So yeah, so I mean, really, if you look at it, 98 to 99, Yankees and Phillies are really, there's not much of a difference. Like less than 1% of a difference between them. Both of them are really good hitting teams. It's just the Yankees did better in a better hitting league than the Phillies, but honestly, they're both really good. But of course, the Red Sox are the best. Okay. All right. Do you want to do another one?
Sure.
Okay. Let's see, what other ones do I have in here? Oh, this is a good question here. Okay. So let's say, I didn't leave out here. So toddlers, age 3 years old. I don't know. This is good. 3 years old. We're going to pretend these numbers are right. So you want to know the probability of finding a patient that's 35 to 38 inches tall, knowing that we know that the mean, I should say, is normally distributed with a mean of 38.72 and a standard deviation of 3.17 inches. Find the z-scores. So in this case, and this is why I hate okay, so we're going to do toddlers age 3 years old. So you want to know the probability of finding a patient that's 35 to 38 inches tall. We know that the mean is 38.72 and the standard deviation is 3.17. Okay. So it says find the z-scores. You need to find the z-scores in order to figure out the probability. But the idea with this one is, this is a good problem because the idea is if we draw our normal standard curve, I didn't know we're orange, but that's fine. So if I draw my normal standard curve, I'll do that a little fast. What is the mean here? What should this value be? Who haven't I picked on for a while? Yami, I think it's your turn.
Okay, the mean would be 38.72.
38.72, okay. And so in this case, we want to know values here, this value. So we've got 35 to 38. So both of these values are less than the mean, right? So I want to find these two values here. This is, if we fill in our little thing here, we want to know this area when they're 35 to 38 inches tall. So what would be that orange area? How would you figure that out?
Would we find the z-scores?
Right. So we need to find the z-score for the big number. I don't know why I've got this on underline constantly. Somebody needs to change their battery in their Fire detector. Smoke alarm. All right, so the Z for the big. Elise, it must be your turn. Can you, so the big number would be which number? Are you still here, Elise? Oh, you're on mute. Can you find the Z-score for the larger number? Did you walk away, Elise? How about Allie? Can you do it?
Sorry, my 4-year-old was simultaneously talking to me. What was the question?
Okay, I want you to find the Z-score for the 38 inches.
All right, so for the Z-score, you start with the 38 inches because that's the number.
Okay.
And you subtract that. Which one is the mean? Because like they're the question marks.
Yeah, so the mean is 38.72.
Okay, so you subtract it from that. And then you divide it by the Z-score, and is that the 3.17? Is that what that is? Okay. And divided by the square root of 1.
Square root of 1 because it's this chapter and we're lucky. Okay. Okay. So 38 minus 38.72, if I plug that in here, equals 38 minus 38.72 and 3.17. So that gives me the numerator divided by the denominator, which is negative 0.227. So we're going to round that to negative 0.23. Okay. So we need to look up that value on our chart. So negative 0.23, negative 0.23, what's that value? Can you see it?
Negative 2.3, it's 0.4129. Wait. Yeah. Wait, no, sorry, that's 1 over 0.4090.
0.4090, okay. So this value here corresponds to a value of, so basically we're saying that 40% of students or of toddlers are 38 inches or less, okay? So now that Ollie did that, let's go to Bridger. Oh, Bridger never answers. Easton.
Yes.
Bridger, pipe in there if you're here. So we're going to do the Z for the small number.
So that one is going to be 35 minus the mean, which is 38.72, divided by the standard deviation, 3.7 or 3.17, and then we're just using square root of 1 for this.
Yeah. Yeah, it didn't really specify. So if it doesn't specify, just assume it's 1. Okay. So 35 minus 38.72. Lost my calculator here. Equals 35 minus 38.72, which is negative 3.72 and 3.17. So we'll take the numerator divided by the denominator. That gives us a value of negative 1. So we'll round that to negative 1.17. And so what value does that correspond to? So what, negative 1.17? Negative 1.17. Okay, so what value is that?
0.1210.
Yeah, it's that one right there. 0.1210. Okay. So this is 0.1210. And so what we're saying here, okay, so we said that 40% is less than 38, and we're saying that 12% is less than 35. So if we subtract those two values, these two values here, okay, then this number minus this number is going to give us 0.288. So 28.8% of students, of toddlers, so the answer is 0.288, or well, I kind of like to leave them as decimal, 0.2880, or 28.8% of toddlers are between 38 inches tall. Okay. All right.
And so that's saying that there's a 28.8% chance of finding a toddler in between those heights.
Right. Okay. So I will post the notes up. I've got a few more examples. Actually, I probably will take those out because some of these use Excel commands. I'll get rid of that. There are a few more examples in here that we didn't have time to go over, but I will post these notes. Chapter 3 homework is due on Friday, right before class. I will make sure those are visible right now. And do you have any questions before I let you guys go?
So on the z-score, do we always round that to 2 decimal points?
Yeah, we do, because that's the way our chart is. So
okay.
You can find it off your chart. Yeah, so always round that to 2 decimals. And then the values in the chart are for 4 decimals, so just use those. Okay, good question. Anything else? All righty then. Well, it was great having you guys here, and we will see you all on Friday. So you've got your homework and your quiz that are due on Friday. So we'll see you all then.
Thank you.
Have a good one. Yep. We'll see you.